Next up, we have Adam from AWS, who is doing a presentation that's sort of...
about 4 hours long.
About 4 hours long. We've gone a little bit over, so he's going to just push on and cover that for us today, because I think it's very important, and I'm actually very interested to hear what you have.
Me too.
Thanks, everyone. Please
Excellent.
welcome Adam.
Thank you. Okay. Okay, good afternoon, everybody. Just before I get started, I just want to pay a big round of applause and thanks to the organisers. Today has been absolutely fantastic. There have been some fantastic speakers, there have been some really good insights, and I have to point out that I've never been to a conference where I got steamed broccoli in a food pack, so I want to call that out, and congratulations to the organisers. It's really, really important, I think. So I do actually have 4 hours of content, which I'm going to try to get into as short a time as possible. I'm going to go quite deep, and I'm going to go fast. And the reason for that is because we've been sitting here all day hearing about all sorts of things about serverless, and I actually want to dive into an actual end-to-end implementation. I'm going to try and walk through the code as fast as I can, but I'm going to make some assumptions that you all know what serverless is by now. You all know the patterns and practices. You've seen various use cases. I'm actually going to run through a live demonstration of building a distributed workflow. And then I've got a pre-built one, which I'm going to walk through the code, given that we hopefully have some time. But I just want to cover a couple of things before we get started. And I'm just going to turn on my clicker. There we go. First of all, I think you'll agree, after everything you've heard today, serverless is a real mind shift. It's a real change of the way that we develop applications. And it's all about agility, and it's all about automation, and it's all about innovation. We've heard many speakers today talk about innovation and changing the way that we think. But there's a few things that you need to do differently when you are using serverless applications, where you're building serverless applications. And I want to introduce you to a couple of tools in the AWS toolkit for creating serverless applications. So for those of you who don't know SAM, the serverless application model, I'd like you to meet Sam. There's the logo. You can get a t-shirt, but not from me. Talk to Buzzy. So SAM is the serverless application model. This is basically a transform on top of CloudFormation. So it's not a different specification. It is an enhancement to CloudFormation. What it does is it allows you as a developer to think in terms of an abstraction. It's a declarative environment, even more declarative than CloudFormation, and it's a transform which emits canonical CloudFormation. So you as a developer don't have to worry about the minute details of CloudFormation, because that can get quite verbose. It also allows you, it comes with a toolkit that allows you to debug locally. So SAM Local is a Docker container that is run on your local machine, and allows you to emulate and simulate the Lambda environment in the real production environment. And so what that means is you can do local debugging even offline on an airplane. You can step through, you can even connect it to Visual Studio Code. You can connect to your Lambda function and step through debug while you're on an airplane. And the SAM CLI tooling, we've just released some updates to that, allows you to even bootstrap your development by running a SAM CLI command. You can actually get it to emit a Hello World blueprint for Java or .NET Core 2 or other languages that are supported, Node.js, for example. So I'm not going to demonstrate that today, but I just want to point out there's some great tooling, and please do check the documentation on how SAM can help you. This is what a SAM template looks like. I'm going to quickly run through this. The very first thing you need to remember is that you need to put the transform. That namespace there basically says to the AWS CLI parser that you want to do a transform using SAM. And once you've got that in place, this is the entire SAM template to actually emit a Lambda function with a, let's just say it's Node 4.3 implementation in a zip file. And it's also going to expose that Lambda function to an API gateway endpoint, which you can see there under events. So it's going to do a proxy front end for all of the HTTP verbs that are sent to that the API gateway endpoint, and send them all to that Lambda function. It's going to wire all that up, including permissions. It's going to deploy the API for you. It's going to deploy the Lambda function for you. And it's even going to make, you can see down the bottom there, it's going to create a DynamoDB table for you. That's a good maybe 16 lines of code. And the amount of effort that you haven't had to do because you're not using CloudFormation directly is enormous. So SAM is going to really streamline your development. Now, I also want to point out one other thing too. There was a bit of a discussion on the panel earlier about some of the, I guess, inconsistencies with the way that we work with serverless today, because serverless is moving so fast and we haven't really kept up as an industry. And one of the things is deployment. So I'm really pleased to be able to say that AWS does have a solution to canary deployments or blue-green deployments. So we refer to it as safe Lambda deployments. It's the ability to do a gradual deployment of a Lambda function in your staging or even in your production environment, which you probably should be doing a safe deployment in your production environment. So you don't need to switch over and then hope for the best. Basically, the way that it works is when you're deploying SAM, normally use CloudFormation, as in the CloudFormation deployment engine will do the deployment for you. But if you, I'll show you the code in a second, you basically turn on safe deployments, and what we will do behind the scenes is we will automatically use AWS Code Deploy to create an alias for that Lambda function, and for all of the traffic that's coming into your Lambda function, we'll send some of the traffic to the new version and most of the traffic to the old version. And then over time, we will migrate all the traffic to the new version. If at any time something goes wrong, it will automatically roll back. So it's a very safe way of deploying your Lambda functions. So this is all you have to do. This is the level of effort for you as a developer in order to use the safe deployments. You need to turn on auto-publish alias. You need to give it the name of the alias. So that's just an arbitrary name live. I could have called it fish or staging or prod, whatever I wanted to call it. And once I've done that, I then need to add in a deployment preference. The deployment preference is, there's a enumerated list of the types of deployment preference that you can use. This is basically saying you want to use a canary deploy of 10% of the traffic every 10 minutes. So it's a very safe and slow way of deploying that change into production. So basically the Lambda function is updated immediately, but only some of the traffic goes, and over time that will make it to 100%. The other good thing too is that you provide some alarms. So you basically say, if any of these CloudWatch alarms fire, the deployment didn't work, roll it back. And that's completely automatic. You don't have to do anything apart from wire up those alarms. And you also have the ability to align, to assign hooks. So you can say, run this Lambda function prior to the deployment, and after the deployment finishes, run this Lambda function. So that allows you to do some testing and some cleanup, and all of this is completely automated for you. If at any point something goes wrong, the whole thing will roll back, and you can run away and fix the problem. So we do have some new ways of doing the same thing that we used to do in a non-serverless environment. It just means that you need to get familiar with the tools. Okay. Now, getting familiar with the tools also means getting familiar with the different way that we're going to create our applications in production. So gone are the days, I think, where you are going to start at an application and create a monolith and intend that that monolith is going to live on forever. Now we are rethinking our application design. If we've got a monolith and we want to move it to serverless, we need, as you've heard the speakers talk about today, we need to peel the onion. We need to look at the low-hanging fruit and take the low-risk parts of our application, peel them out, run them in a serverless environment, and then over time we're going to migrate our entire application across to serverless. So what we're going to end up then is some complexity. We're going to end up with functions which used to run in the same code base calling each other. Now they're calling each other across the wire. To me, this is the new normal. Distributed complexity is the new normal, and it means that we're going to have some various challenges that we're going to need to address when we're designing our applications. Am I going fast enough for you? I'm looking at you. Okay, so let's talk about a couple of key things we need to resolve in order to, or challenges we need to resolve in order to make our applications distributed. First of all, how do we handle transaction state? So if we've got a transaction that's executing at the moment in the context of a monolithic application or a monolithic data store, that's pretty easy. Begin trans, end trans, that's all good. But if you've got a distributed application, you're probably going to, in fact you should be using polyglot persistence as far as the data store is concerned. So in a microservices world, every microservice should own its own data store, and there shouldn't be any shared data store state across those microservices. So therefore you're going to need to deal with eventual consistency. You'll make a change to one data store, and that change needs to replicate through your system. So in this diagram here, you see that there is a call coming into a Lambda function. That Lambda function is causing various events to fire through your system. What if one of those Lambda functions writes to a data store and it fails for whatever reason? Maybe it's a business logic problem, maybe it's a data store problem. You need to roll that back. But now you've got all these moving parts. How are you going to resolve that? That's not done automatically for you. You, as a developer, need to think about the asynchronous calls and the eventual consistency in your distributed application. What about if you wanted to create a workflow where you have multiple running tasks which take an indeterminate amount of time? So we know that we have some constraints on our serverless environments on the various cloud platforms. It can be 5 minutes, it can be longer, but there's always a constraint on how long that serverless function is going to run. What if you've got a workflow which needs to run for a year? Okay, so what are you going to do about that? How are you going to handle that? And how are you going to handle retries and failures in that environment? How are you going to keep state through that entire period of time? Also note that some of the failures can be transient. So you've tried an action and it failed, you need to back off and try again a little bit later. But they also may be completely fatal. You can't recover, or they may need manual intervention. So there's various different modes that you need to cope with failure. The next challenge is the coordination of tasks. So you're actually going to create a distributed workflow which has various behaviours based on the way that the calls are made through your application. And so the tasks that are involved in that distributed application are going to be distributed across multiple systems. And again, you need to keep state and transfer state from one part of your application to the next. So how are you going to get visibility into exactly what's going on in your application? So that's what I want to talk about today. How do you orchestrate this distributed application, and how do you get visibility into it? Okay, so let's talk about how we could solve this if we wanted to roll up our sleeves and write it ourselves. The first thing you could do is consider function chaining as a way of coordinating your application. So in this diagram, Lambda function A calls B, calls C, all the way to F. Now the problem with this, while it will work, is you've got some dependencies here. Lambda function A needs to know explicitly about Lambda function B, and B needs to know about C. It needs to know what to call next. The problem with this is that you've actually got your application chaining logic built into your source code. So if you need to make a change, for example, you need to, for Lambda function B to call Lambda function F, you're going to need to redeploy those Lambda functions. So you really need to think about taking the orchestration or the coordination of those functions outside of the code base themselves. Let's look at it another way. What if we were to use a single source of truth, a distributed locking system? So maybe we have all these Lambda functions that periodically wake up and they call into a DynamoDB table to see if they can obtain a lock or a mutex. The good thing about this is that it's running on the Amazon DynamoDB, which is highly available and very efficient. But again, you need to have some business logic built into your application. So if you wanted to change the way the data flows through this system, you're up for a redeploy. What about this one? I do love SQS, as I'm sure most of you do. This, again, allows me to use AWS managed services, which are highly available. But, again, I need my Lambda functions to know about each of the queues. And if I want to change the way data flows through this, I need to redeploy my Lambda functions. Putting aside the fact I could actually use a configuration in each of these Lambda functions, I still have to change my code or change my configuration in order to make a change to this model. So it's not ideal. So if we were going to fix this, what would we do? First of all, if we're going to have a coordination and orchestration system, we must have scale out. It needs to be able to handle that 5 billion calls per second that we were talking about during the keynote. It needs to not lose state. It needs to not lose state, yes. It needs to be able to run for a long time and handle errors and retries. It needs to be able to handle exponential backoff. It needs to be really easy to build and define and deploy. I don't want to have to write any code. I want it to be declarative. It needs to be automatable and auditable, and it needs to be visible and traceable. Well, luckily, I actually have a solution for you. This is AWS Step Functions. So AWS Step Functions is a fully managed service that makes it easy to build distributed workflows or distributed applications. And it's designed specifically so that you can declaratively define the behavior of your application and implement it using microservices. So you're basically constructing a state machine. So your role as a developer is to define the state machine and then provide the code for each of the states and let Step Functions manage the flow of data between each of those states. So if you wanted to change the way data flows through your application, you change the definition of the state machine, not the code itself. So we need to drop down a level now because we're going to run through a demonstration. We need to understand what are the options that we have with each of the states in the step function. First of all, we can run tasks in parallel. So basically spawn multiple Lambda functions, wait for a result, and then continue on. We can add an if-else or a when-otherwise, basically a choice state. We can have catch and retry, so we can actually detect that there's an application-specific error and branch, or we can retry with exponential backoff. We can put in a wait state, so we can say, look, I want you to wait here for 30 seconds or 3 months and come back a little bit later. And we can also have a pass state, or basically a no-op. This one is really important for debugging, as you're going to see in this first demonstration. So I'm going to build this. This is a simple calculator. This is a little bit hello world, but it's going to touch a lot of the features of creating a state machine. I'm going to create basically a simple arithmetic calculator that handles add, subtract, multiply, divide, and also handles errors. And first of all, it's not going to do anything. I'm just going to create the state machine from scratch, and then we're going to come back on the second demonstration and implement the actual logic. So let's just drop back into the, oops. Okay. Gee, it's quiet in here. Okay. So So here is my AWS console. This is my state machine, or my step functions console. I'm going to click Create State Machine. Now, I'm not going to write this from scratch because we don't really have much time. I have pre-created the state machine definitions, but I'm going to walk through it so you can see what it looks like. Okay, so by the way, I'm using the Cloud9 IDE here. So I'm able to, I can't demonstrate this today, but I'm able to deploy my Lambda functions using a right click. I'm able to do step 3 debugging using SAM local, which is built into Cloud9. I've got syntax highlighting and auto completion and all sorts of great stuff. I'm sure there's plenty of opportunity at the next Serverless Days to do a full demonstration of Cloud9, not today. So you'll notice that the state machine is actually defined as a JSON payload. So a couple of things. First of all, there is a start at node. The start at node tells the state machine which of the states in the collection is the entry point. So you must have an entry point. And here is the states collection. And the first state that I've got here is called operator selector. Notice the naming convention, start.state.operator selector. Completely arbitrary. My brain works like namespaces, and using dot notation makes it easy for me to read, but I could have called it cat if I wanted to. So as long as they're unique, each of the states can be called whatever you like. This is of type choice, so I'm going to do a branch here, and I've got a collection of choices. So this is basically saying it's looking for a variable, and if out of the input data, the root of the input data, which is what's defined as $, if the input data has a .operator property, and if it happens to be a string and it's equal to add, then I want to branch to the next state being state.process.operator.add. Okay, so if I look for that definition down here, there it is. Oops. State.process.operator.add is of type pass, so this is a no-op. I'm just doing a debug for the moment. I have a comment there, so it's human readable. It will then pass state to the state.process.displayResult, which is defined down here. Display result is again of type pass, and it passes to state.complete. Okay, so pretty simple stuff. Let me just drop over into my state machine. I'm going to give it a name and call it simple calculator. And hopefully I have paid it forward by thanking the organisers, and the demo gods are not going to bite me. Okay, so there we go. So all I did was I dropped my JSON payload in there and I pressed refresh, and I've got a visual representation now of what my state machine looks like. So you saw that in JSON, but let's run through it again. I have my operator selector. If the input data has an operator property and its name is add, or its value is add, then the state machine will branch to this state. If it's subtract, it'll go to this state, etc. And then they all will converge on the display result and then complete and end. So let's have a look at, let's firstly make sure I press create, yes. Let's have a look at the actual payload that I used to design this. So this is it here. It shouldn't be a surprise. Out of the root, we have an operator property, and for this demonstration, it's going to be a value add. And then we have a series of operands. In this example, I'm not using the operands. That's the next demo, but bear with me. So I'm going to copy that into my clipboard, go back over to step functions, and I'm going to run an execution. So you can think of an execution as an instance of a state machine running. I'm going to paste in my input, so operator add, and press start. Immediately the state machine is, it's already finished. It's executed, and you can see the path that it took. First of all, we started off at the start node. It went into operator selector. Operator selector decided that the input had an operator property of type add, and then it branched into the add handler, then down to display result and complete. So there was no processing done there, but I've actually been able to debug the logical flow through my state machine. Let's run that one more time. This time I'm going to add in a different operator. So let's say subtract. And what we should see here again, immediate execution. Operator selector decided that the operator value was subtract. It's dropped into the subtract node, down to display and complete. And just for completeness, let's do it one more time. This time we're going to put in some junk. So an operator called junk, which is not defined. And what we should see here is that it's correctly branched into the error state, which you can see there. So I've now been able to detect that there's an error, invalid data, and branch accordingly. No, it doesn't actually do anything at this stage, but I'm able to very easily debug my, my business logic through my state machine. Okay. So we want to point out a couple of things. It's very easy to get started. A couple of things that you need to know. Obviously, it's a JSON payload, and you can deploy what I just did there using the AWS console, can be done via CloudFormation and also by the SDKs and the CLI, so you don't need to use the console itself. Every state is named it must be unique, and the naming convention is arbitrary, but there are some constraints on the naming convention. It must be a start point, so that's how the state machine knows where to start. And each state in the states collection must be a type of either choice, pass, parallel, wait, fail, etc. Every state must have a next state if it is not fatal. And by fatal, I mean it's not marked as error or end. Okay, so there needs to be a flow through the graph. And also, if you define a task, which we're about to do, in that example, the type was of type pass, which didn't do anything. But in the next example, I'm actually going to supply a Lambda function that is going to implement each of those states. And therefore, I must declare what the resource is, the resource that should be called in order to fulfill that particular state. You can also have tasks implement a retry. So in that case, I had a failure which exited immediately, but I can actually have a retry clause as well, which will allow me to do exponential backoff and retrying of the function. And the reason we'd want to do that is because imagine if you were using a state machine that was calling out to an API, and that API sometimes got overwhelmed, and therefore you needed to call it, like, wait for a little bit and then try it again, and eventually it came good. Well, if you were to do that in a monolithic application, you need to code that yourself, and you need to keep state, and you need to, all that heavy lifting you need to do yourself. But in the case of a state machine, it's really easy. Notice the clause that I can put here, retry. So this is basically saying that if the error that is encountered at runtime is of application defined, so it's completely my choice what the name of the error is. If it's my transient error, I mark it as having a maximum number of attempts to retry. So that in that case, it'll try 10 times to hit that function again. I can also add in a wait state or a delay. So basically implement an amount of seconds to wait before retrying and then exponential backoff, number of seconds to add each time I try. So in this next example, I've actually, because I love Polyglot, and while I am a recovering .NET developer, and then they introduced .NET Core 2, and I'm like, oh, okay, I'm back there again. I also speak Java and Node. So all of my demos today, I've got a .NET example, a Java example, and a Node example. So hopefully I've covered everybody except the Ruby people and the Python people in the room. So in this example, I'm actually implementing it in Java, and notice the function declaration there. So this is the entry point for my handler. It is a function which is throwing a random processing error. That's completely my definition. So the way that you actually tell the state machine that you have thrown an error, or that there is an error state, is you basically just throw out of the Lambda function. So you're basically throwing across the wire. And so what I've implemented here is just a silly example because it's very hard to make this thing fail. So I've implemented a probability of failure, and I've set that as an environment variable. So when the application starts, or when this particular calculation starts up, it is going to randomly guess a number, and if that happens to be within the probability of failure, it is going to throw an exception. So hopefully, one of the times I run this, it is going to fail. I practiced this just before, and it wouldn't fail at all. So this could go. Hopefully, that's my only failure in my demo. Okay, let's have a look at how this is implemented. So first of all, I'm going to edit my step function, and I'm going to, rather than write this myself, I have one pre-baked here, and I just want to point out the changes. Again, we have a start at, no change. Again, we have a collection of choices, and we have our default choice down here if none of those match, which is the unknown state. And again, we're branching to each of the operators. Now, if I go to the add operator, the add operator is defined, it's a little different now. It's of type task. It's no longer of type no-op, or pass, I should say. And it has a resource. Now, that resource is a Lambda function, which I have previously deployed. So we don't have to go through that process. The Lambda function is implemented in Java, and I'll look at the code in just a second. And then notice the retry clause there. I'm basically saying that if the error equals my dot notation, I develop.exceptions.random processing error, then I want to wait for 1 second and then use exponential backoff of 2 seconds. So it'll have an additional 2 seconds each time it runs for a maximum of 2 times. That's all I have to do to define that exponential backoff. And I've defined the same thing for each of those various states, so subtract, multiply, etc. So let's take that definition and drop it into my state machine to edit it. Again, I could do this using CloudFormation by just updating my SAM template. Okay, so that's now done. So let's, before we run it, let's have a look at the code. Oops. Okay, so here is my calculator handler. Hopefully that's big enough. This is the code you just saw before in the PowerPoint. So let's skip the probability of failure. All I'm really doing here, I'm logging out some stuff, and then in my inbound request, I've created my own request model. I'm calling getOperator, and getOperator is just looking at the type of the operator field in the inbound payload. And if it is of type addition, then I'm creating a brand new addition operator, which is implementing a calculate interface. So I'm basically just using polymorphism there to make my code a little bit nicer. And then basically down here, I'm saying for each operand in the inbound collection, down here, for each of the operands, I call calculate. So I end up iterating through each of the operands in the array and calling calculate and then setting a result. So it's pretty easy stuff. So let's see what that looks like if I run it. If I get my... I'm going to do a multiply of all those numbers. So I can click Start Execution, paste that in. And again, I can do this programmatically, of course. Run the execution. Okay, good. So what we're going to notice here is it's gone into the start node, it's dropped into the operator selector and correctly determined that it was multiply, but now it's sitting there doing nothing. In actual fact, it's not doing nothing. The random processing error has fired and it's doing a 1 second wait and then it's going to retry. Okay, now it's finished. So this is polling in the background. So it's automatically done the retry and then exponential backoff for me because it's thrown a random processing error. But how do I get visibility into that? How do I actually know that's what's going on? If I click on the item itself, see down the bottom here, I've actually got a list of all of the entry and exit points of each of the steps, when the Lambda function started executing, when they failed, or when they succeeded. So full visibility there of exactly what's going on. And you can see here, the Lambda function failed here. And if I open that up, I can actually see my random processing error. So that exception that I threw in my Java code has thrown across the wire over to the step function and has been emitted into the step function log. So full visibility to exactly what's going on, including how long each of those steps took. So if I just zoom this back, you can see here that starting at the 0 state, 158 milliseconds after the, 158 milliseconds after I clicked Start Execution, the Lambda function had already failed, and you can see that wait state there. That's actually that 1 second delay. So very visible on exactly what's going on. It then retried the Lambda function second time. Luckily, it worked, and then it's passed out to the end. Let's run that one more time. This time with a with a divide, just to prove that it can divide. And this time it probably won't fail. Yep, straight away it's executed. So you can see how fast the state machine is, and it's called the Lambda functions. It's orchestrated everything for me. I don't need to have my Lambda functions calling in to the state machine in order to work out what to do. The Lambda functions are called automatically by the state machine. And again, if I scroll down here, I can see all the ins and outs, the time. So the entire process of calling all those steps and the Lambda function to do the calculation was about 400 milliseconds. So really nice visibility that I've got there into exactly what's going on. Okay, so let's take that into the real world. What if we wanted to use AWS step functions to create a real application? That was great for a hello world. It's good to get some exercise on a simple example. But what if we wanted to use this tool to create a toll road gantry number plate parsing system? What would we need to do there? So let's say the problem statement is that we want to extract vehicle number plates as the vehicles pass through the gantry, and we want to be able to distinguish between various different types of error. Okay, so the way that this is going to work is that we have an S3 bucket that we have a camera with a motion detector, and which I don't have with me, but trust me. The files are automatically uploaded to an S3 bucket, and we have an S3 trigger, which is an event-based model for firing off a Lambda function whenever an object is put into the S3 bucket. The S3 trigger is running a Lambda function, and I'm making use of Amazon Recognition to extract the number plate on the car as it drives past the gantry. So Amazon Recognition, you've heard a little bit about today. It's a fully managed service for feature extraction and classification of objects and faces and celebrities and text out of images and video. So I'm using that in this example. So there's a couple of conditions that I need to be able to handle. If the text looks like a number plate, okay, so it looks like a number plate because maybe there's lots of writing on the car, so we need to be able to grab all the text we can see in the image and then run it through a regex to basically say, yep, that's a number plate. If it looks like a number plate, then we want to charge the driver associated with the account. If the driver has insufficient funds, we need to notify the driver they need to pay us money, and we need to put the workflow into a wait state. If the driver has sufficient funds, we want to charge them straight away, obviously. Now, if the number plate isn't registered, so if it's some rogue driver who's driving through the gantry and doesn't have an account, then we need an administrator to step in or an operator to step in and maybe talk to the vehicle registration people and say, hey, can you find out who this person is? We need to charge them. And the last possibility is, apart from general failure, the last possibility is that what if the AI system is not confident that it read the number plate properly? Then we need a pair of eyes to look at the image and say, yep, actually this is the number plate. So this is my architecture. So on the left-hand side, you see we have the Amazon S3 bucket. So the camera is uploading the files to the S3 bucket, and that's triggering the Lambda function. The Lambda function is grabbing the details of the image on the S3 bucket and passing it to Amazon Recognition and asking it to detect text. At that point, we have enough information to kick off the workflow. So we actually call into the step function. So there's no way to kick off the step function directly from the S3 trigger. You need to use the Lambda function in order to do that. And as it turns out, we wanted to augment the data anyway, even if you could trigger the Lambda function, the step function directly from S3. So the first thing it's going to do is it's going to decide whether or not there was a number plate in the inbound payload at all. So it's going to make a decision. If the answer is yes, so we are on the left-hand side there, then we branch down to the number plate detected state. And if the number plate's detected, then we try and charge the driver, which is basically going to be deducting $5. It's a very expensive toll road. $5 from the DynamoDB table associated, for the record associated with that particular driver. If at that point they don't have enough credit, we then need to branch into a fail state, which is going to require that manual intervention. The other option is that, yes, we did see a number plate, but we have no record of the number plate, therefore we branch down into the unknown number plate error on the bottom right there. So you can see it's quite a complicated workflow, and yes, you could code this into a monolithic application, but if you wanted to change the behaviour of this at some point after it's been implemented, then you would have to redeploy the code. But in this case, all I need to do is just change the step function definition itself. Okay, so this is the way, I showed you in that previous example how I was doing a retry with exponential backoff, but in this case, I want to branch if there is an error. So instead of using retry, I use the catch option. So what this is basically saying is a collection of application-defined exceptions that can be thrown, and what the catch clause does is it says if the error happens to equal exactly unknown number plate, then it will branch to the next state, which is the state.error.unknown number plate error. Again, completely application-defined naming convention. If the error happens to be insufficient funds error, then it'll branch into the insufficient funds state. And then finally, notice how we define a catch-all. So states.all is a predefined keyword that basically is the same as default in a switch statement. So that would then drop down into general exception. Now, I need to clarify something because I showed you the demonstration with the calculator earlier, and the calculator, I had no op first, or a pass state, and then I added a task state with a resource, which was a Lambda function. But a task is a unit of work, and it can either be a Lambda function, which we will call automatically when the state is entered, when the step function enters that state, or alternatively, you can define an activity, and an activity means that any compute anywhere in the world on any cloud platform or off cloud can poll the state machine to ask if there's any work to do. So that means that you can use this to implement out-of-band processes, for example, manual intervention. You can have the state machine running for up to 1 year, and therefore, in my example, you can basically have 1 year for the operator to log onto the system and disambiguate the image if the AI system was unable to determine the number plate, or even up to a year to chase the driver for their $5. Now, what you need to do in the activity that implements this is that you need to call send task success or send task failure through the AWS API, which is available through the SDK in all the languages we support. So you just need to make sure you do your work and then call either success or failure, and then the state machine will kick off to the next step. So this is how we're implementing the manual steps in this particular workflow. So this is what it looks like. In the state that happens to be an activity rather than a Lambda function as defined as a task, then rather than using the Lambda function ARN, the Amazon resource name, you use the ARN of an activity. And you can just create as many activities as you like. They're basically just placeholders. The state machine will stop there until somebody calls send task success or send task failure. And then if the send task success is called, then the next state will be entered. Now notice here, number plate path selector. If anyone who's paying a lot of attention might be thinking, hang on, that's the entry point of the entire workflow. Well, that's exactly what I've done. I've created a loop. So if the driver has insufficient credit, then we go into a wait state until they pay the money, and then we loop back into the step function and let it rerun again, this time with more money in their account. So I don't have to create any edge cases or special cases in order to implement that wait state for up to a year and then rerun the state machine. All of that is handled for me just by my state machine definition. Also notice that there is a parameter option for heartbeat seconds. So this is basically saying the agent that is polling and calling into the step function, it must, in this case, it must call in every 60 seconds or at least every 60 seconds. And it must call send task heartbeat. And if it doesn't, then the state machine will fail. The reason we do that is because if you have a 1-year running task and it falls over, the poller falls over 1 day into that 1 year, you don't want to wait for 364 more days to find out that the state machine failed. You actually want to know straight away. So if the polling agent doesn't call in every 60 seconds, then the state machine will fail. Okay, so we're using this to wait for a manual task to complete. The polling agent can, as I mentioned before, can be on cloud or off cloud. You can use a Lambda function. In fact, that's what I'm using in my case. I'm using an AWS Lambda function to call in and call getActivityTask, which is the API call you need to make, again through the SDK, to work out if there's any work to do. And at that point, it's up to your application definition to decide what that work actually is. So in my case, I'm going to send an email to the administrator or the driver. So if it's the number plate doesn't exist in my database, I need to call the administrator. If it's a known driver and they don't have any funds, then I'm going to email the driver to give me some more money. What I then do is I send them a link to a website. Now, in this case, just because I wanted to show off a little bit, I've implemented the website behind Amazon API Gateway, running a .NET Lambda function, .NET Core 2 Lambda function, running Razor templates. So the entire website itself is serverless. I'm not even hosting a single page web app. Everything is running in .NET, running on the Lambda function, and it's launched just in time whenever somebody clicks the link. So that website shows the image of the uploaded number plate. So the user can look at that and go, yep, I think that's what the number plate is, and then disambiguate that text. So as I mentioned, I'm using .NET Core Razor templates, and all the other Lambda functions in here are going to be Node.js. Now, unfortunately, because we are running behind, I'm not going to be able to step through everything. So I'm going to just show you the highlights of the code. But more than happy to talk in more detail over drinks afterwards if you'd like to know more. Let's look at this from an architectural point of view, just so we're all clear on exactly what's going to happen before I run the demo. So I'm using Amazon CloudWatch to run a schedule event once a minute to call into my AWS Lambda function to kick it off, and it will automatically call getActivityTask of the step function. So it's basically waiting to see if there are any state machines that have a wait state waiting for that manual intervention. So let's say it was the manual inspection. So we need an administrator to look at the image to work out what the number plate is. Let's say that's the example. So in that case, we generate a email notification using Amazon SNS and send that out to the administrator. With a link, when they click on the link, it hits Amazon API Gateway, which has a Lambda function behind it, which is running that .NET implementation I mentioned. And then when they type in the actual number plate and hit submit, then that fires back into the Lambda function, which will then call into send task success of the step function and kick the workflow off again. Now, before I show you the demonstration, I just want to talk one last bit about visibility and traceability in this distributed system. Because as you can see, and I am talking very fast, but there is a lot of moving parts in this. So how do I know what is actually going on? How do I know if my code is performant? How do I know if I'm wasting cycles and therefore wasting money in my implementation? So this is where we need some really good metrics and basically APM in our application. So to get those insights into the distributed application, we will be using AWS X-Ray. So X-Ray is a fully managed service which allows you to get insights into your distributed applications. So basically you are, by declaring that you're using X-Ray in your application, for example in Java, it's just a matter of putting the X-Ray recorder in your POM file and building, and then everything else is handled for you. All calls that are made through the AWS SDK and between each of the services themselves, so when AWS Lambda calls S3 or recognition, that's automatically traced for you, and you get to see a visualization of that. So it's a great way to see the dependencies in your application from an AWS services perspective, but also you can inject your own metadata at any time. You can create your own subsegments at any time, so you can time parts of your code if that's something that you're interested in doing. So it allows you to get a really nice end-to-end cross-service view of the calls that are made in your application. This is what it looks like, the service map. So you see down the bottom here, I have my AWS Lambda function on the left. That's the call that's coming in. The second Lambda function there, so the first one is actually the AWS side. We're responsible for firing up your Lambda function. And the second one is your code. So you can actually see how long the AWS cold start time is by looking at this graph. And you can then see on the right-hand side that we have 3 calls that are being made from that Lambda function. One is to the S3 bucket, one is to recognition, and one is to step functions. So really nice visibility in there. And if there are any errors, you would actually see those appear as different coloured circles. So you can see visually whether or not you have any issues with your application. And this is, if I wanted to drop down into the trace view, and I will actually zoom in on this when I get into the demonstration, but vertically down the screen there, you can actually see all the calls that are being made and exactly how long they're taking. And so if I wanted to fine tune, for example, I can see there that the upload trigger is taking 830 milliseconds to run, and the bulk of the time is actually in the number plate processor itself, which is taking 622 milliseconds. So I might want to focus on that part of my code and see how I can optimize that and reduce the amount of time that it's taking. So I've got really nice visibility into exactly what's going on there. I've completely lost track of time too, so make sure you give me a... yep, 1 minute to go? Okay, good. Or is that a thumbs up? Thumbs up, okay. Okay, so let me give you the demonstration first. Here's my S3 bucket, and I have some pre-canned number plates. So first of all, I'm going to, actually my DynamoDB table. So I'm using DynamoDB as my system of record for the users in my system. And my partition key is basically the number plate. And they each have an email address that I'm going to email, which happens to be my email account, because otherwise it makes the demonstration difficult, and how much credit they've got. So what I'm going to do is, this number plate here, SSS650, has $29.50 credit. So let's upload that one, and let's see the happy path. So I go to my S3 bucket, SSS650, drop that in, and upload it to my S3 bucket. Now, in a real system, that would automatically be uploaded. Okay, so once that's uploaded, I'll go back to my step function, and we can see that at 3:45, so this is Melbourne time, sorry, 3:45 and 37 seconds, so that was just now, the step function has been processed and succeeded. So if we have a look and see what actually happened there, so we came into the start node, we jumped into the number plate path selector, it determined that there was a number plate in the image, and then it's charged the user and completed successfully. So if I go back over to the DynamoDB table, so $29.75, if I press refresh, that should have dropped by $5, which it did. So that automatically charged the user for driving through the gantry, as simple as that. So let's try something a little more complicated. Let's say we upload an image for a vehicle that is not registered. In fact, it's not even a number plate. Let's go that one. So this is a number plate, but it's not, the regular expression would reject it because it doesn't look like an Australian number plate, so I've intentionally used this one. So let's upload that, and we go back over to our step function, and we can see now we've got a running state. And that's running because if we drill into it, it's going to be in a manual intervention required state based on my application definition. So the number plate parser has detected that, that we need a manual decision. And if we look, we've actually got quite good visibility here, because if I drop into what the input was, oops, this is the input that came in through my S3 trigger. So I know the bucket and the file that was uploaded. And see how it says detected false? That is my Lambda trigger, which is worked out, as I'll show you the code in a second, based on calling into recognition. It got the number plate, then it ran it through the regex, which is my regex parse there, and it said, no, this is not a number plate that I recognise, so I actually need an operator to intervene. And that's why we've gone into the manual decision state. So if I go over to my email, and we can see today at 3:46, which is just now, an email was sent to my account. And if I open that up, I have an email to the administrator, which is me, and it's basically saying, you can click on this link and see the number plate. There it is, that was what was captured. And what I need to do as an administrator is I need to click on this link, and notice the URL is Amazon API Gateway, and this is hitting the Lambda function, which is written in .NET Razor template. So there is my application. I can look at that and say, okay, I'm going to lie here because it's part of the demonstration. Actually, the number plate was SOB640 and press submit. So I've now injected additional metadata into the workflow, and the state machine will now re-enter and try and process that number plate based on the operator-defined data. Now what we're going to find is, if I go to SOB640, which by the way happens to be my number plate, I didn't choose that for any other reason, this driver only has $1.34 credit. So therefore, we've been notified that my account is exhausted. So we have an error over here telling me, your number plate was detected driving through the gantry, you need to give us more money. Okay, so if I go back over to my step function and look and see what state it's in, we can see here, it's automatically updated. So it dropped over into number plate detected once I typed in the number plate and pressed submit. But now it's checked against the account, and now it's dropped into insufficient credit. So I've re-entered the state machine, and this time it's taken a different path. And no, I didn't have to code any of that. It's all based on the configuration. Okay, so this time I'm going to pay some money. So I'll click on that link. And again, this is coming out of that Lambda function. I'm going to give it $5 credit and press top up my account. And what we should see over here is, okay, the state machine is now finished. That could have taken up to a year. In actual fact, it couldn't, because I set the timeout to 5 minutes in this particular demonstration, but state machines are allowed to run for up to a year. So all I've done there is I've let the AI system determine the number plate, and when it couldn't, I've augmented the data and re-entered it. And again, the state machine, the step function definition, is controlling the orchestration of the flow of data through that system. Let's look into the, how are we going for time? 1 more minute. Okay, so I'm not going to drop into the implementation. I just want to show you a couple of very quick things. This is Visual Studio for Mac, which is really awesome. There's my alarm. This is how, when I press submit on that Lambda function web page, see the code there, whoops. I'm making an async send task success async call. Basically, that is the call that's calling back into step functions and providing additional metadata, whatever the user typed in. That's how I'm kicking the step function off again. So it's a simple one statement call there. And the other thing I wanted to show you, given I've only got 1 minute, is how does recognition do the initial work. So this is my S3 trigger that runs, oops. And why is there no code in there? No, do not save that. Oops. Okay. Quickly show you how I actually do the number plate extraction. So down here I am basically just calling recognition detect text. 1 line of code. If that succeeds, then I will get a collection of text detections, which I then iterate through each one of them, and I check to see whether it looks like my regular expression. And if it is, then I remember the number plate string and then inject that into the payload. And then the way that I start the step function itself, if I come down here, I basically call step functions.start execution and provide the execution parameters, which happens to be my incoming payload. So it's only a couple of lines of code in order for me to wire up the Lambda function to recognition, extract the data, and then create a payload, and then hand it on to the step function. So pretty easy. Now, one other thing I need to show you before I go, because I want to talk about X-ray, and that is that notice that I had this X-ray capture async func here. This is the way that Node does it, but there are different ways of doing it in the various different languages. What I wanted to do there is I wanted to inject my own timing mechanism, because I want to know how long that block of code takes. So all I need to do is declare that this is basically a callback, so obviously everything in Node is asynchronous. So I want this function to be called, and I want X-ray to capture how long it takes to execute. So I can basically just create what we refer to as a subsegment at any time in my code. So I've actually called it ServerlessDays Auckland detect number plate in captured image, and that will appear in my X-ray log. And then all this work here is being done automatically for me, but I can inject my own metadata. So any data I think might be important while I'm doing debugging, or that I want visibility to inside X-ray, I can just call add metadata or add annotation, and I can inject that data in. So what that ends up looking like, if I jump across to X-ray, and if I say, give me an update please of the call graph in the last 5 minutes, which it's now doing. And that was a bad example. Let's make it 15 minutes. And and there we go. So down here is the Lambda function call. That's actually Lambda being loading in my code, and then here's my code execution here and the functions that it's calling. It's calling the S3 bucket, it's calling recognition, and it's calling step functions. And if I jump into this, I can actually see each of the calls. So let's take the one from here, and you can see that metadata. So this detect number plate in captured image, that's my segment that I created, and that whole part of code is running for 550 milliseconds. So at any point, I can inject my own segments, and if I click on that, we can actually get to see the metadata that I injected. So in my particular case, I wanted to know what was the bucket, the key, and even the regular expression that was used to determine whether or not this was or wasn't a number plate. So completely up to you to add your own metadata in, and I have to keep moving on. I'm actually finished, but just before I jump off stage, before the big hook comes out and pulls me aside, a shameless plug. I run a developer enablement program in Australia and New Zealand a couple of times a year. I'm running it in Auckland on the 3rd of July, must book my flights, and Wellington on the 4th of July. We're going to be talking about applying the 12-factor app manifesto to serverless. So probably quite relevant to this group today. Please come along. It's I think this time we're running it at 5 o'clock, and you never know, there might be beer and pizza. And mixed with other developers who want to hear about this, and it's a great opportunity to network. Go to that QR code, which will take you to the website where you can register. And with that, thank you very much for your attention, and I hope you enjoyed that very fast run through of AWS step functions and AWS X-Ray. Thank you very much.